Art, I'm really curious what you say.
Okay. Yeah, thank you again for the invitation. Yeah, Wojtek and Philip asked me also just name some future directions, and I thought I'd name just some directions which I think might be nice to look at. So the first one is actually about a paper by Andre, who's in the audience. And I really liked it, and so I think this is a direction that would be worth studying more. So I call this infinite state systems in the service of arithmetic, because I mean, you probably all know that one way to prove that Presburger arithmetic is decidable is using finite by observing that all the languages that you can describe, all the languages of binary encodings are regular languages. But this breaks down very quickly. I mean, this still works if you do Bishi arithmetic, then you can still do this proof method. But for example, it doesn't work anymore if you do Seminov arithmetic, which allows you to have a function that maps any number to number n to 2 to the n. So far, methods based on languages have not worked for Seminov arithmetic, but nevertheless, this is decidable. There's also a notion called generalized Seminov arithmetic, which was introduced in that paper, I believe, where you have Seminov arithmetic, but you also have regular relations, which means you can have relations on numbers, so you encode a tuple of numbers, each of them you take a binary encoding, and then this is an input to your multi-tape automaton. If this multi-tape automaton is synchronous in all the components, then that's a regular relation of numbers. So that's generalized Seminov arithmetic. And the paper I wanted to mention is by Dragici, Hase, and Manea, this year at Stacks, which shows that the existential theory of generalized Seminov arithmetic is decidable in exponential space. And I thought this is nice to mention in this particular workshop because they use VAS techniques. So they encode the existential fragment. You can imagine that if you do the Presburger proof, you can reduce it to intersection of finite automata. That doesn't give you the right complexity, but nevertheless you can use it. And they do something similar but with VAS. And I think this is a very nice approach. And I think right, and this also gives you the existential theory of some structure of words, which I don't want to go too much into. Maybe Andre can do that. But I found this inspiring, and I think it would be worth studying how can we use all the things we know about VAS and other kinds of automata to solve questions about arithmetic. So for example, if you imagine you have a counter where you can check non-linear quantities, for example, is it a power of 2? Or is one number divisible by another? I know almost no results on whether things like this are decidable. And you can imagine 1,000 different ways of doing this. You can add this to a VAS, you can add it to I don't know, a push automaton. I think there's really a lot we don't know. And many of these, whatever you write here, possibly leads to a nice theory of arithmetic. Another thing is, maybe you have a stack where you could only do pushes, but then you check nonlinear properties on the represented numbers. So for example, you can push zeros and ones, and then you have a predicate that checks, is this a prime number or is this a float? Okay, power 2 would be boring, but the point is if you take something that doesn't fit the view of a binary encoding, then you get some interesting questions. Yeah, that's basically everything I have to say about this. Yeah, another direction where I think infinite state systems could be useful is in the service of word equations. So a word equation is something like this. You write an equality between two expressions where you can use capital letters, which are variables, and small letters, which are seen as concrete letters. And then the solution would be a word over A and B that you plug into X, Y, and Z so that what you write there is true. And people have looked at word equations for many, many years. Originally, this was thought of as a way, so Markov thought that proving word equations undecidable would be a way of showing that Hilbert's 10th problem is undecidable. But it turned out the other way. Word equations are decidable, and Hilbert's 10th is still undecidable. So that failed. So they were studied for a long time. And length constraints have been looked at since the 80s. So length constraints allow you to say that two variable contents have the same length. And it's been open since they've been introduced whether word equations with length constraints are decided. So it's known that if you do slightly more sophisticated things like counting letters, you can say this word has the same number of A's as this word, then this becomes undecidable. But with length constraints, we still don't know. And I wanted to present, not really present, just mention a recent result where you can use infinite state systems to make progress on this. And to present this kind of as another direction. So it turns out word equations with counting inequalities are decidable. And a counting inequality is you take a function that in some sense is given by an automaton, I don't want to get into details, and then you can say things like this function has to be non-zero. So if we could do that with equals 0, then we would have solved the length constraints problem. But the key here is, since we ask for not 0, this can be done. And I think questions like this could be studied more. So the way we do this is we use a result earlier that says the solution sets to word equations are EDTOL languages. And EDTOL languages and slices. And EDTOL languages are known to be languages of pushed-on automata with higher order steps. And we show that you can, given a second order pushed-on automaton, you can compute the smallest slice containing the Pareto image of that second order pushed-on automaton. And when you can compute the smallest slice containing the Pareto image, it means the Pareto image is for any other given slice, you're contained in that other slice if and only if the slice closure is contained in that. So if you have the slice closure in your hand, you can check inclusion into any given slice. So in particular, the one that says f is equal 0. And that's how you can check existence of a solution that's not equal to 0. Right, and I think this kind of pattern can probably be repeated if we understand the models that describe solution sets. So we know it's EDTOL, but it could very well be that there's a closer approximation of these solution sets that give us more decidability properties. So it's known that if you just try naively to check if a given EDTOL languages, if it satisfies f equals 0 for these things, then this is undecidable. So in that sense, this is not the right abstraction. So I think it's worth understanding infinite state models that can describe these solution sets, but still have more decidability properties. Right. And then, of course, study the algorithmic questions on those models. And the other thing is bidirected reachability. There's many open problems. So I mentioned that for bidirected one-dimensional p-VAS, we know it's in p-space and it's p-hard, but we don't know the exact complexity. The complexity of bidirected p-VAS, we know that it's in Ackermann and Tower-hard. Then decidability in general bidirected valence systems. And this is, of course, it's an even more difficult problem. But so what you would need to do is, so in other words, that would mean beyond p-VAS, you would alternate building stacks and adding encounters. And the reason specifically this is interesting is because this would in particular solve, as far as I can tell, a very important open problem rule theory. Because there's this class called right-angled arcing groups, which correspond to valence systems where you have on the graph self loops everywhere. And then, as I mentioned on Monday, the bidirected reachability is the same as the subgroup membership in the corresponding groups. And so far, there's only a sufficient condition known. So if the graph is chordal, then we know that the subgroup membership problem is decidable. But there are fixed graphs for which it's not known whether the subgroup membership is decidable. If you take a circle on pi nodes, then nobody knows that it's decidable. But I could imagine that using slices, as we have for p-VAS, could be used. So in the results, the group theory that exist, they also use ascending chain conditions, but on Abelian groups. And slices, in a certain sense, generalize Abelian groups, and they also have an ascending chain condition. So I could imagine that slices are the right notion to attack even this group theoretic problem. Then of course there's bidirected math with less than zero tests. Maybe can we still do it in exponential space? That would be nice. Disequality tests. Mutual reachability, yeah, I think this is less interesting since I know that in PVAS mutual reachability is already as far as the whole thing. But of course you can look at this in all these other forms. Right, and then something about application. So there was a nice observation in the paper at PLDI 20. So as I mentioned, bidirectedness was looked at by people who do static analysis. And they motivated bidirectedness as a speed up for general reachability. They did not notice the connection to vector addition systems at all, but they just proposed this as a practical approach. You can take any infinite state system that has a sensible notion of bidirectedness and look at every edge that exists. And then you check bidirected reachability in a path that uses that edge. And if the answer is it's not reachable, then you can forget about that edge. You make your system smaller that way. And I mean, there's no guarantee that this actually helps in practice, but it's worth a try. Okay, that's what I have.
Any questions, remarks, additional open problems?
Well, yes, I have a question about B-directed VAS with nested zero test. Do we have some complexity bounds? I mean, do we know something? Or it's completely open? Or?
I haven't thought this through, but I would expect that you can again reduce it to PVAS, and then you would get the upper amount.
Okay.
But sometimes these reductions are deceptive in the bidirected case. Sometimes they break in unexpected ways. We have to carefully think through. It probably works, but I don't promise.
Okay.
So it's like it's a special case of a PVAS, right? So it's.
But that's not so clear. Probably.
Yeah.
I mean, usually you can reduce nested zero test to PVAS, but bidirected.
Maybe not in a bidirected way.
Yeah, the reduction might not preserve bidirectedness.
I have a question that might not fit in here. Do we know the decidability status of stuff like bidirected two-stack pushdown?
That's undecidable.
Undecidable.
There's one direct proof by Pavlokianis and Kjellström, and we obtained it independently via group theory.
Oh.
But their proof is more direct. The group theory it uses deep results that it's not so easy to understand. I would use the Kjellström Pavlokianis paper.
Are there any other part of math where you see some applications of infinite state systems and vectorized systems except of proof theory and because the example that you mentioned,
Arithmetic.
what?
Arithmetic.
And that makes sense.
And I mean word equations. So I think the thing about word equations, so something Richard is working on, for example, is equations in other structures than, so these would be equations in the free monoid, right? Words in the free monoid. But of course you can look at equations in other groups. That's what Richard is working on. And there you can basically do the same program. You can try to understand what the solutions look like. And can you use infinite state systems to decide something like this system does?
Any other question? Okay, so thanks, Georg.
Maybe one more question. Have you ever seen someone trying to do some kind of equations for languages?
Yeah. There's a lot of work on language equations. Alexander Obotin, Johanni Kaoriti, Arthur Jesch. There's a lot.
Okay,
Mihao Kung or Kunz, I don't know what's his name. So there's a lot of non-trivial work on equations in language. So you just take the Minkowski product of languages, you factorize